Welcome and thank you for the opportunity to discuss our developments at Freeform Fibers and our work on the Navy Strategic Systems programs. Direct to Phase 2 Small Business Innovative Research Program shaped high strength silicon carbide fibers for CMCs in hypersonic applications made by LCVD. We are a company built along a unique technology platform, laser chemical vapor deposition, or LCVD. CVD is a common practice for high performance thin films, practiced in the microelectronics industry for decades, with literally dozens of possible material combinations available. Joseph Pegna, our lead co founder, developed the ability to focus the energy required for CVD conditions, extreme thermal gradients, using laser power, which enable to growth of fibers as opposed to thin films. Our approach, developed initially in an academic setting at Rensselaer Polytechnic Institute, then moved to the University of Montreal, was spun out into a company in 2006. The co-founders represented over half the industry and academic practitioners and experts in LCVD. Our current president and CEO, Shay Harrison, was practicing LCVD separately during his PhD research at the University of Connecticut. He became familiar with Dr. Pegna and his work nearly 30 years ago when it was still an academic curiosity. After starting his career in the ceramics industry, he joined Freeform Fibers as their materials scientist in 2012, rising to his current role in 2020. The company has focused on demonstrating high-performance ceramic fibers in a range of material formulations with a focus on non-oxide ceramic fibers as improvements over the state-of-the-art in the fibers used in the ceramic matrix composites industry. In addition to the technical expertise in LCV, the company has extensive product and market experience in their key target market segments, including carbon-carbon materials for nose tips and nozzles, for example, ceramic and graphite powders and processing, and ceramic matrix composite materials and processes. Freeform Fibers has been chartered with producing domestically a novel ceramic fiber, shaped silicon carbide. Currently, silicon fibers are primarily produced in Japan by two manufacturers, Nippon Carbon and UBE Industries. Both are derived from polymer precursors, which are pyrolyzed to create the silicon carbide backbone. Polymer approaches require unique ingredients to catalyze the pyrolysis reaction, which lead to an inability of their silicon carbide fibers from achieving the optimal performance desired. Laser CVD, on the other hand, produces stoichiometrically pure fibers, as the only ingredients are the gas precursor decomposition byproducts, which chemically react and then deposit to form the fiber. The thermodynamics of the deposition conditions controls the ratio of silicon to carbon in order to achieve properties as close to the theoretical properties of silicon carbide. Once incorporated into a composite, in particular silicon carbide fibers embedded in a silicon carbide matrix, a phenomena that would require a mini course in micromechanics occurs. A silicon carbide matrix by itself in a monolithic form has exceptional strength, stiffness, and specific gravity properties and performs up to 2,100 degrees centigrade. However, a monolithic silicon carbide component can be very brittle and unable to withstand significant thermal shock or multiple cycles of heating and cooling. Adding fibers to the silicon carbide composite is designed to not augment the strength and stiffness, as is the case for polymer matrix composites, but to enhance thermal shock resistance and damage tolerance. However, in order to not detract from the properties of monolithic silicon carbide, fibers need to not fail in a brittle fashion, but serve to deflect cracks as a means to absorb energy in the event of failure. In order to achieve this crack deflection, the state of the market is to add an interphase coating to silicon carbide fibers, usually a thick layer of boron nitride or pyrolytic carbon, which weakens the interface between the fiber and the bulk ceramic. This creates fiber pullout, or rabbit holing, where the fracture surface is not smooth but very rough and jagged, indicating the absorption of energy via crack deflection along the fiber matrix interface. A shaped silicon carbide fiber is expected to provide a series of benefits over a smooth, constant cross-section fiber. First, the irregular cross-section may provide the type of crack bridging phenomena without the need for an interphase coating by limiting the ability of fibers to slide past each other in a failure mode. In addition, the shape design, based upon diameter variations and node spacing, may lead to better fiber packing efficiency in a composite. Both of these would lead to major cost reductions in the way silicon carbide fiber, silicon carbide matrix composites are produced. The goal of this project is to model, optimize, produce, and test these shaped fibers to validate those concepts. In today's market, where high temperature ceramic composites are used, you generally find limitations based around two phenomena: the brittleness of the desired ceramics to perform at elevated temperatures, whether monolithic or reinforced with a toughening component such as ceramic fibers. Materials which do perform temperatures up to 1200 degrees Celsius require novel processes, which are expensive and difficult to consistently repeat in a manufacturing environment, whether using chemical vapor infiltration, melt infiltration, or polymer and powder approaches. In order to achieve a level of fracture toughness required for both single use and repeated cycles at the intended performance temperature, you often need to include an intermediate layer to deflect cracks at the fiber matrix interface. This is a phenomena unique to carbon and ceramic matrix composites, as opposed to polymer matrix composites. The use of interface coating to create a crack deflection layer between the reinforcing fiber and the matrix ensures cracks are deflected at this interface, creating a pull-out or rabbit hole-looking appearance. These interface coatings are typically based on a boron nitride composition or a pyrolytic carbon layer. The goal of producing a shaped silicon carbide fiber is to assess the impact of the irregular cross-section of the fiber can yield to the same type of crack deflection and energy absorption as an interphase coating without the extra cost and consistency concerns of the secondary coating. The solution created by free-form fibers is to produce an economic, scalable, shaped silicon carbide fiber. The fiber cannot sacrifice the properties typically associated with existing silicon carbide options. Modeling of fiber cross-section variables, framed by the knowledge of the fiber growth process enabled by laser chemical vapor deposition, will identify the optimal shape and periodicity of the shaped silicon carbide fiber to create a new family of toughened ceramic matrix composites. Understanding that one of the goals of a Phase 2 SPR is to achieve a technology readiness level, or TIRL, the company has commenced a milestone-driven development project to achieve Level 6. Accomplishments in modeling, characterization, prototyping, capacity expansion, and pilot-scale production have been achieved and are on target for success. Commercial-scale production of the optimized, shaped silicon carbide fibers, accompanied by fiber and composite testing to verify desired properties, is on track. Benefits of this development are twofold, based upon improving the mechanical properties and toughness of brittle ceramic thermal protection systems. The LVCD process offers high-fidelity control over processing parameters that can control material compositions and fiber geometry, including varying diameters. For this proposal, short silicon carbide fibers of varying compositions and shapes will be produced, characterized, and down-selected for large-scale production based on their high temperature and high strength performance. Enhanced thermal shock resistance of high temperature composites extends the performance range for a variety of manned and unmanned vehicles, benefiting the warfighter. Demand across multiple Navy platforms, as well as cross-agency needs with Army, Air Force, and MDA. The Navy and DoD would benefit from having a domestic supplier for this important material. Freeform Fibers has invested significantly in developed commercial relationships at levels ranging from academic to industry prime contractor to test, characterize, and further evaluate our materials. Focusing on Department of Defense prime contractors, these relationships include Raytheon, Lockheed Martin, Northrop Grumman, and Boeing. In addition, Materials subcontractors who supply the system prime contractors such as Exothermics, TDA, ATC, and SINTX have been engaged for materials and processing support, ranging from sample preparation to testing and analysis. These subcontractors will also help pull through these materials advancements to the system's prime contractors. With positive testing and characterization results, a transition to the Navy fleet would follow normal materials qualification and implementation protocols. The market assessment of potential commercial applications includes commercial penetration of ceramic matrix composites utilizing silicon carbide has been limited, with specific niches in the oil and gas industry, high temperature glass, metals processing, and other unique performance needs. The primary market will remain aerospace and defense, where silicon carbide fibers in a matrix of silicon carbide or other higher temperature ceramics such as hafnium diboride or zirconium carbide are currently used. Commercial aviation does utilize silicon carbide composites, although the current market is dominated by a vertically integrated supplier, a propulsion system OEM. The transition path involves a multi-step business model plan aligned with our company objectives. The projected business model is to continue to build awareness at the Navy DoD level and work with systems prime contractors and leading materials fabrication subcontractors for research, development, testing, evaluation, characterization, and scaling, suitable test articles, and prototype parts. The objective of freeform fibers is the transition of the technology to make shaped silicon carbide fibers to supply a program of record with appropriate qualification steps. The company's goal is to be a domestic supplier of critical materials with unique properties produced via a technology that is patent protected. To wrap things up, we are a small company that is investing in our future. We have achieved ISO accreditation, preparing the operations for meeting the needs of a program of record. Please feel free to contact us, whether Shay Harrison, our President and CEO, or Jeff Vervleed, our Director of Sales and Business Development. You can also find company news and updates when we are allowed to share them with the public on our website, www.fffibers.com, or our LinkedIn page.